We are ready to start the second part of Physics Controversies, Past and Present. And the first talk of the afternoon is going to really keep us awake. And is going to be on the scientific history of cold fusion. Is Dr. Michael Loughlin of ITER organization, but you're not speaking for ITER.
Yes, that's right. I'm talking about cold fusion today. Just a little bit of background. I worked for ITER, which is an international organization based in the south of France, where we are building a magnetic fusion device. But I won't be talking about that. So what I will be talking about is cold fusion. So on the 23rd of March 1989, a press conference was held at the University of Utah. I was coming back from a conference in Venice. In fact, it was the first paper I presented about measuring neutrons from fusion reactions. And I stopped off in Paris, staying with a friend above a betting shop where he had his apartment. And he told me, he broke the news to me by saying, "I think you're out of a job." So these guys, Martin Fleischmann and Stanley Pons, announced that they had produced a sustained fusion reaction in what was essentially an electrolysis experiment with using palladium electrodes and heavy water. And this news traveled around the world like wildfire, caused a tremendous lot of interest. Strangely, looking back now, by the end of May 1989, so just a couple of months later, the scientific community had reached a consensus that there was no truth in any of these claims. And in spite of the fact that these claims were outrageous, I would say, impossible, and they were supported by flawed and possibly fraudulent evidence, and the scientific community no longer is interested in these experiments, somehow it has entered popular culture and the controversy still persists. So we'll have a look at, I'll give a couple of ideas of why I think this is the case. Now, these were, essentially, they made such a huge splash when they made this announcement. And this, the reason I call this an unscientific history is we'll see the many ways in which they contravened the conventional scientific behavior, which includes peer review, the reproducibility, openness in terms of your experiments and so on, things which were mentioned in the talks this morning, in fact. But this, going to the press, in the absence of people who could be a bit more skeptical about what they were claiming, meant that the news traveled very quickly. And secondly, it was nuclear fusion. So this is a shot from the Spider-Man 2 film. A Dr. Octopus loses his mind after spending 30 years with hot fusion research. So it's quite realistic. Yeah. Now, one thing I want to clarify is that nuclear fusion is often listed as one of the most important scientific challenges of the century. But I want to make the distinction. It's the power generation through these nuclear fusion. Nuclear fusion itself is well established. You can do it on accelerators. It's used in many applications, for example, in the oil industry and so on, for neutron sources. But it's the power generation which is the technical challenge. And why is it so important? It does have the potential to provide sufficient power for the human race for many thousands of years. It avoids the problems of climate change and the buildup of radioactive waste, but also it is notoriously difficult to achieve, and in spite of some early mistaken claims, we're still a few decades away from realization of a power station. So what is fusion? Well, it's the joining together of atomic nuclei accompanied by the release of energy and the creation of new elements. And I'll just briefly explain what the difference between fusion and fission, because I do sometimes get asked this. So this curve here shows the amount of binding energy per nucleon in a nucleus. So of course, the nuclei of elements are made of protons and neutrons. At the top end, you have uranium with 92 protons and lots of neutrons. And at the other end, obviously, hydrogen, the simplest element. Now, if you, in fission, well, I should also say this curve is the binding energy per nucleon, and this is the number of nucleons in a nucleus. If you can split the uranium nucleus into some smaller nuclei, you've got this slide down this slope here, essentially shows the energy that you release. At the other end, if you can join hydrogen or deuterium or tritium together to make helium, you get a corresponding release of energy. And this is, we're working in this region, and this is the conventional fission way. So the isotopes of hydrogen. So just quickly, of course, there's normal hydrogen, just a proton for the nucleus, deuterium, 1 proton and 1 neutron, and tritium, which is radioactive with a half-life of about 12 years, and it doesn't occur naturally in nature to a large extent. If you look at the probability of the reactions of these different isotopes to fuse, this is summarized in this graph here. The blue curve shows the DT cross-section, so this, if you like, is the probability of the reaction, and the horizontal curve essentially is the temperature. And you can see that the DT reaction is much more likely, about 100 times more likely than the DD reaction, which is the green curve. Now, in something like ITER, we would be using the DT reaction, and through the power of the internet, I found this little animation here. So the tritium and the deuterium join together. There's an alpha particle emitted and a neutron, and it's the neutron that takes away some of the usable energy. And this goes back to perhaps the most famous equation in physics, E equals mc squared. I have a suspicion that this photograph of Einstein has been photoshopped. I can't really imagine him standing there in front of a classroom and saying, okay, pay attention, E equals mc squared. But this is the crucial equation to much of what follows. So Flashman and Pons, get back to them, they were concerned with deuterium fusion. They had put heavy water into their electrolysis cell, so it was only deuterium. And there's sort of 3 possible reactions. The deuterium can form helium-3 with a neutron. No, we say high-energy neutron. After John Butterworth's talk this morning, I'll have to call it a low-energy neutron because it's only 14 MeV, not a GeV. And then another branch, which is equally likely in all the experiments that's ever been done, where we've been able to measurements, a tritium is produced in a proton. There is a third reaction where the 2 deuterons join together with the emission of a gamma ray. So this last one is extremely unlikely, as we know from experimental measurements. Now you have to remember all of these reactions to understand the way the evidence was assessed from Flashman and Pons experiments. Now, why, just very briefly, why is fusion so difficult, and why is cold fusion so controversial? Well, the positively charged nuclei naturally repel each other because of the positive charges, and if you compute the energy to bring these say two protons together within the range of the strong nuclear force, you would find that it needs an enormous amount of energy, in fact more energy than would be available in the sun, for example. And you have to make recourse to quantum tunneling. This is a weird quantum mechanical effect, and the analogy is, the one way to describe it is, imagine you have a wall, and you can throw a ball at the wall, and if you give it enough energy, it can rise over the wall and go to the other side. If you don't have enough energy for the ball, it will hit the wall and it will bounce back. Now, that's classically speaking. In quantum mechanics, there is a probability that the ball will go through the wall and appear on the other side. and in a manner which is, there's no analog in classical view. If you make the wall thinner but the same height, particles of the same energy are more likely to get through the wall. And if you keep the wall thickness the same and make it higher, particles of the same energy will still get through, but with a smaller probability. Now, all of this was used to explain the way the sun makes its energy. It's all very well understood. And it was known that in a system such as heavy water or in a palladium deuteride system, there is no way that the particles could have sufficient energy to get over the barrier to get over the Coulomb barrier. There were some early attempts at cold fusion, and these were done generally before, certainly before the strong force was understood. I think before the neutron had been discovered and so on. In the Germany of the 1930s, there was a demand for helium for airships. It was after the disaster with the hydrogen-filled airship. And two scientists, Paneth and Peters, loaded hydrogen into palladium, and they thought that they had created helium. And then John Tanberg in Sweden, he heard of their results, and he loaded hydrogen into palladium using electrolysis. And he too thought that he had made helium. In fact, it was not possible. In fact, the helium that they detected had been absorbed from the atmosphere. And at the time, there was a review of these experiments carried out by the likes of Rutherford, and they concluded that in all cases, the presence of an element was mistaken for its creation. Interestingly, Tanberg tried to patent his invention, but he was denied by the Swedish Patent Office. And we saw earlier on that it was in 1932 when the British Patent Office made rules about what they considered to be unrealistic inventions, and John Tanberg was denied because of the retraction of Paneth and Pert when they realized they'd made the mistake, and simply because Tanberg couldn't provide a feasible explanation of what was going on. Anyway, why palladium? When I was rehearsing this talk with my friends, they said, is this like the London Palladium where you're trying to pack people in with... Strangely enough, it's 30 years since somebody made that joke. So, anyway, well, hydrogen has a great affinity for. Palladium has a great affinity for hydrogen, so you can pack it in. The structure looks a bit like this in the palladium crystals, and the hydrogen, symbolized by the red sphere here, can occupy the spaces between the palladium atoms. Interestingly, if they do this, they are further apart than they are in the D2 molecule. And I know from personal experience that a gas bottle of deuterium is not warm and does not emit radiation. So the whole idea, in fact, is a non-starter. Having said that, cold fusion works. In atoms of the deuterium molecule, the nuclei are too far apart to fuse. But if you replace the electrons in the molecule with the heavier muon, the nuclei are brought closer together, partly because the mass of the muon is 270 times more than the electron, but also, and so it provides some Coulomb shielding. These brings the nuclei close enough together for the strong force to catch them. And this has been demonstrated with deuterium and tritium, which are easier to fuse than just deuterium. Now, the problem with this method is that the muon has a half-life of 2.2 microseconds, and its mass is 100 MeV, and the 1 dt reaction yields only 17.6 MeV. However, when the nuclei fuse, the muon is thrown off because of the energy of the reaction, and it can go on to create other muonic atoms. And so there is a possibility that it could catalyze this reaction, and this was the promise. However, other losses mean that it needs to catalyze about 1,000 reactions, And one difficulty is the muon. When it comes off, it has a tendency to stick to the alpha particle, which is a product of the fusion reaction. And in experiments, they only catalyze 250, which is, it's a factor of 4 away from break-even, which is close, but unfortunately, it's not enough. This was explored in the 60s and 70s. There was not a big controversy about muon-catalyzed fusion. I think because the experiments were done carefully, they were reported properly, they were peer-reviewed and so on. Now, back to Fleischmann and Pons. I looked on YouTube at the original press conference, which is available there, and what is quite striking is they were so confident in what they were talking. There was seemed to be very little self-doubt. They claimed hundreds of hours of sustained nuclear fusion reactions. They said this energy production exceeded what could be possible from chemical reactions. They even gave as an example some apparatus which was vaporized. They detected neutrons and they detected tritium. And this is really what made people sit up, because you can do an experiment, but this looked like they had some interesting evidence. They did say at the time that the levels of tritium were too low to explain the amount of heat that was generated. This is a bit strange, because it seems to me that the energy was too high, so we had to overthrow 50 years of nuclear physics. But the levels of neutrons they detected were too low, and that was something that they would just sort out later. They gave this presentation with no prior scientific review, and having watched the press conference and heard some of the things they say, it really wouldn't have got very far at all if they presented it to nuclear scientists. Well, why did they do this? Well, I think it's because of principally because of these two gentlemen. So the guy at the top is the president of the University of Utah at the time, Chase Peterson, and the other guy is Steve Jones of Brigham Young University. He got embroiled in all of this, but I think he was pretty much an innocent party. Chase Peterson, on the other hand, is a more interesting character. In 1981, a dentist from Seattle with a congenital heart condition volunteered for an experiment with an artificial heart that was being developed at the University of Utah. And for 112 days, he was kept alive on this machine. And Chase Peterson, Dr. Chase Peterson, was giving regular television interviews about the progress of this guy. This guy was in a constant, Barney Clark, the patient, was in a constant state of confusion, in terrible pain, and asked to be allowed to die on a number of occasions. Chase Peterson, on the other hand, was regarded as somebody with great prospects, possible senator of the future. Anyway, 9 years later, he's president of the University of Utah, and when two scientists from the university, or one a consultant, one a scientist, came with this potential earth-shattering discovery, he encouraged them very much to have a press conference. Partly because of Steve Jones. Now, Steve Jones worked at Brigham University, not far away, and he was asked to review a funding application from Fleischmann and Pons. And I think quite honorably, he declared he had some interest when assessing this application, because he was also working at looking at fusion at room temperature, but in his case it concerned the generation of, or the discovery of the presence of helium in the Earth's crust. So he declared his interest and spoke with Fleischmann and Pons, and they realized that they were working towards the same thing. But unfortunately, somewhere along the way, although they made an agreement to release papers on the same day, on the 24th of March, to Nature, it was felt by the University of Utah that they had to make an announcement beforehand so that they could establish priority over the claims. And when you look at the press conference, half the time is Fleischmann and Pons explaining the technical details of their discovery, And an equal amount of time is with Chase Peterson discussing how much money can be made for the state of Utah and the university. Interestingly, later on, when they were trying to find funding from the state and from the federal funding, an anonymous donation was made to the research. But it was subsequently discovered that this came from the university. It wasn't an independent donation, and it was Chase Peterson who was responsible for using university funds to feed into the cold fusion research and use that to try and get further support. And he resigned from the university in 1991. Anyway, with regard to the evidence, they said that there were neutrons significantly above background. So now I'm going to go through all the various bits of evidence rather quickly to show how there was nothing in these claims at all, and perhaps how this could have all been avoided. They said that they had found neutrons. There was some question about what energy the neutrons should be. If it was deuterium fusion, it should be neutrons with an energy of 2.5 MeV. And in fact, these were not detected directly, but via absorption of hydrogen, or absorption in hydrogen, and then the measurement of the subsequent gamma ray. In Frank Close's book, Too Hot to Handle, which I would recommend to anybody who wants to have a detailed history of all of this, Frank Close says that the tide began to turn when Flashman gave a talk at Harwell, and a nuclear physicist pointed out that the gamma rays were at the wrong energy. That person happened to be my section leader at the time, and he came back and to tell us what had happened. I'll go into a bit more detail about what went wrong with that gamma ray energy later. Anyway, there were neutrons. Immediately after this announcement, people were very excited. They went to do experiments, and without proper care, they then reported to the press if they found a positive result. Irving Langmuir, in his study called Pathological Science, gave some of the characteristics of pathological science, and one of them is that positive results always come first. And there's a good reason for this. If somebody makes an announcement like this, and you try to repeat it, and you don't find anything, you're going to check very carefully before you make the announcement, because you're going to have to stand up and say somebody is wrong. On the other hand, if you do an experiment, you find positive results, it seems almost natural to say, oh yes, we see it as well. So it's natural that there should be some positive results coming first. It's human nature. Another characteristic of pathological science, according to Langmuir, is that the results are at the limit of the statistics. And many of the measurements of the tritium and the neutrons and so on are right there. And I would add that as the experiments improve, they always stay at the level of the limit of statistics. And you never see them rise up out of the statistical noise. Now, it turned out that the people who first announced these neutron measurements, they hadn't taken into account the effect of temperature effects in the neutron counters. So it was just a case of people with little experience in doing these measurements making a mistake, and they retracted. A more interesting case was at the same time, some colleagues of ours who worked in Enea in Italy tried to do something slightly different. They took titanium and packed it with deuterium at cryogenic temperatures, and then put a neutron detector next to it to see if they could see any neutrons. And this, when I was looking through my paperwork, I found this old photocopy, and I just thought I'd point out that you see the different people's names. As we photocopied the paper and then passed it on to the next guy, you'd write your name on it, and you'd cross the previous guy's name out. Interestingly, on Chinese paintings, you often see red stamps like this, and sometimes you see a whole series of them. They're the different owners. They put their stamp on the painting when you see it. So in the days before emails, when we had faxes and photocopiers, this is the type of thing that would go on. Anyway, this is the signal that the people from Enea thought they had seen. And what we have here is we have the time axis along here. We have number of counts, and they saw over a period of about 1,000 or 800 minutes the neutron counts rise up and then gently drop away. Now, these were colleagues of ours, and we were intrigued by this. And at JET, we had a very similar system, the same type of detectors, but we had 6 of them in an array. So colleagues at the Atomic Energy Authority produced some titanium rods with deuterium in and cooled them down. And we dropped them into our array of detectors. And one evening, there was one of us, a guy called Piet van Bell, was on his own, and he saw the counts start to rise in one of the detectors. Now, partly because we had 6 detectors and there were only counts in one of them, so he was pretty sure it wasn't a real signal. If neutrons were being produced, it should have been in all of them. And also because he was very skeptical of the whole thing. So he ran into the lab, grabbed the rod and pulled it out and walked away, and he saw that the signal carried on. Now, if he'd have been wrong, he'd have had a neutron source in his hand and he was walking around with, but he had the courage of his convictions. And in a way, a bit like cutting the Gordian knot, he demonstrated that it was not real. And in fact, it was condensation on the electrodes of the detectors, because we had this cryogenic titanium. This caused shorts in the detectors, in the wiring. And this illustrates another point about the scientific method and reproducibility. We saw exactly the same signal as the people in Italy, and it's because the temperature was the same, the detectors were the same, the condensation is the same, the rate of evaporation, the breakdown in air and so on. It's all the same. It doesn't matter where you are. These are the laws of physics. And so the fact that we could reproduce it and explain it meant that they could go back, they found the same thing, they made sure there was no condensation and the signal never reappeared. This lack of reproducibility, of course, was something which has plagued all of the cold fusion experiments that there have ever been. Now, the other evidence was the neutron measurement. Now, this is the actual data that was initially presented and sent for publication, and you can see that the peak is centered on, beg your pardon. The peak is centered on 2.5 MeV, which is the energy of the neutron which comes out. Unfortunately, the process by which this gamma ray is generated is that the neutron goes into the water, say of the cell or the surroundings, and loses energy as it's scattered and is absorbed in the hydrogen. So hydrogen plus a neutron makes deuterium, E equals mc squared. The energy out is not 2.5 MeV, but 2.2 MeV. And it was my section leader who pointed this out to Fleischmann. And the next day, the peak had magically moved to 2.2 MeV, with no explanation as to why this was. There was never any consistency. And you can see it's actually the same data. You know, it's not another measurement or anything. It's just the same data, and they've rewritten the scale. What was quite controversial at the time as well was that Fleischmann and Pons didn't share their data with anyone, and it was a bit difficult to extract what was going on. And eventually, the people from MIT published a paper in Nature where they examined the gamma ray spectrum, but they were only able to get the information by getting VHS tapes of a press conference in which the computer with the gamma ray spectrum on was shown. And they did a screenshot of it and then analyzed the spectrum. And by looking at this, they were able to establish that the so-called peak couldn't possibly be due to gamma rays. This diagram I took from Frank Close's book, but it's in the paper there as well. In a real gamma ray spectrum, there are certain characteristics that you should always see. You see a peak with a certain width. You see this ridge here, if you like, which is the Compton edge, which you should also always see because it's related to the physical processes of the gamma ray. And you can also see another secondary peak, which is always 511 keV lower energy to do with the escape of a positron from the detector. And you can see that the original peak doesn't have any of these characteristics. So clearly this is something else. Probably noise in the detector, but certainly not a gamma ray. Anyway, So now here's a photocopy from The Guardian of the 11th of May. So remember, the initial press conference was the 23rd of March. On the 11th of May, we have this article. And it's there in the text, but you can see that Flashman says, "We are well aware that the peak is wrong. It disturbs me greatly. Without such an emission, the claim to have discovered a nuclear reaction taking place at room temperature in a test tube cannot be sustained." So you can see now Flashman himself is more or less conceding that the game is up. That followed several retractions. There'd been some tritium measurements claimed from the University of Seattle. There'd been a rather interesting experiment they'd done where they'd set up their electrolysis, and they had a mass spectrometer and they drew the gas off, and they found mass 6 molecules in their mass spectrometer. So they interpreted this as this could only be tritium. Tritium has a mass of 3, deuterium, and hydrogen. You can't make a mass of 6 unless you have 2 tritiums joined together in a molecule. However, they'd overlooked the possibility that you could have ions which were stable in the form of HD2 plus or D3 plus, also have a mass of 6. And in fact, this turned out to be the case. Interestingly, Johnson Matthey of the UK had supplied the palladium. And when people asked Flashman and Pons, could they do an analysis to see if there was any tritium originally in their palladium? Because Flashman and Pons hadn't done any background measurement. The results were promised, but when the time came for the results to be released, Flashman said, "No, I can't do it because they haven't been peer reviewed yet." Anyway, so the other thing that the heat, well, there was this apparatus which exploded. There's a famous, or well-known, rather, effect when if you load hydrogen into palladium and you don't maintain the voltage and it starts to leak out, energy is released and then the hydrogen can ignite. And somebody made a cigarette lighter based upon this effect. And an apparatus exploded in Los Alamos, and they were able to establish that this is exactly what had happened. In Flashman and Pons's case, their exploding apparatus there was no witness, nobody knew what had happened, and they just assumed it was a nuclear explosion. Oddly enough, nobody was killed. The other criticism in terms of the heat measurement is they were asked frequently what happens if you use ordinary water instead of heavy water, which would have proven it was nuclear fusion, or at least disproven it was nuclear fusion if they saw extra heat. Flashman's response was, first of all, to say, we didn't get the baseline we expected, which meant that they was getting heat in ordinary water, and then subsequently they refused to answer any questions on the matter. While all this was going on, Flashman was helping Harwell to conduct a set of experiments. So he was advising them, making sure the apparatus was exactly as it should be and so on. And you see, by June the 19th, so this is the newsletter that we used to get when I was at JET. See? So you'll see in the text that by this time, results up to date have been disappointing, and we can no longer justify further devoting further resources in this area. So the most careful set of experiments being done at Harwell were abandoned by the 19th of June. The helium, again, they claimed that helium was detected. Funnily enough, they didn't know enough about the chemistry of helium, and if it's produced in the palladium, it's bound to helium, and you should never be able to detect it escaping the apparatus. So in fact, the helium that they saw was some contamination of the experiment, and as was said in the 1930s, the presence of an element was mistaken for its creation. So just finally, there was another more recent incident where people thought that they had developed fusion, not so much cold fusion, but perhaps a lukewarm fusion in sonoluminescence. This is an effect where you can take a liquid, you set up a standing sound wave in it, and if you can seed a bubble, you can hold it in place, and then with another sound wave you can cause this bubble to oscillate, and it will emit light. And somebody made the observation that this was a star-like luminescence, which led somebody to think, well, could we get fusion in it? And Russi Telyakin of Oak Ridge National Laboratory published a paper in Science saying that he'd achieved this. At the same time, the University of Los Angeles were very skeptical of this result, and they set up a corresponding experiment where they tried to produce it. And what they did was they had more sensitive equipment, and they tried to correlate the flashes of light with neutron emission and found no results whatsoever. One of the reasons behind this may be that the Department of Defense, who were very interested in the production of tritium, had said that the first person to demonstrate fusion from sonoluminescence will get a grant of $100,000. This might have encouraged people to be a bit too hasty. In the end, the neutrons that Telyakin claimed to have seen were probably just due to backgrounds. Anyway, so in conclusion, the implausible claims, let's make this clear, the claims by Fleischmann and Pons are completely without foundation. There's no evidence for cold fusion whatsoever. And in fact, within 2 months, the scientific consensus was that there was exactly that. As far as I know, they continued to believe that their experiments would be vindicated, but all of the furore and the waste of time and money and the ends of people's careers could have been avoided if the scientific conventions had been respected. A good experiment, of course, will always trump a theory. Anyway, thank you.
So I just have a comment that Russi Telyakin was actually a professor at Purdue University after Oak Ridge, and he was a distinguished professor, and after a further examination of his paper and the fact that he said that some student did some work and the student didn't do some work on the paper, in fact his distinguished professor was revoked, and it caused a lot of acrimony also at the university level at Purdue with this story. Anyhow, questions?
Thank you very much. Can you speculate or report on other people's speculation as to the motive that drove the two academics to this?
Yeah. What drove them to it? Well, I think it was. I think when the apparatus exploded, they were probably quite physically shocked, and they thought that they were onto something. But I think after that they then, when they heard that Steve Jones was very close to demonstrating the fusion could work at cold temperature, the administrators encouraged them, I think, to go public with it, purely to get priority over it. Fleischmann himself felt he was rushed into it, but the behaviour of Pons was a bit controversial, you might say, because his lawyer sent a letter to people asking them to withdraw a paper from Nature which demonstrated that no radiation was coming from the apparatus. And that was some time afterwards. So I think Pons was convinced that it was right, and it was just a matter of time before the proof would be available.
Do you think they were genuine with this guy?
I can't say. At some point, they must have known that something was wrong. Moving the gamma ray peak without any explanation, for example. I mean, it's.
More questions?
Do you think out of all this is coming the fact, I think we sometimes like to think that science is pure, everybody does it for the best motives, and there's a scientific method and everybody's striving for the same thing. But do you think, as scientists, people suffer from the cult of the personality as much as anybody else?
Yes, I think that something like Popper's view of science and so on, is almost, that's the perfect model that nobody adheres to. And the efforts that the people at MIT went to extract information from the TV screen and so on, showed a level of determination which I think was not entirely explained by a search for scientific truth. On the other hand, they were vindicated. I mean, they were right. They showed that there was something was up, and that's okay. And it's, I don't know if it's, I can't speak for other areas of physics, but certainly in fusion, there is a very high degree of examination of what you're saying. I mean, you are scrutinized to the letter, you know? And so, to some extent, there are people who don't want you to succeed. At the same time, there is, it's because it's so important, you have to be pretty sure that you're right when you make a claim.
Oh, there is a question over there.
Sure. There's one down here as well.
Mine's a very quick question. When you get a controversy like this playing out so publicly, what's your take on what that means for the public perception of science? Is it damaging, or is it actually encouraging when they see that science actually writes itself in this way? What's your view?
People have said it's good to see the way science works, to see the examination. I'm not entirely convinced that what was done was turned out well. I've been involved in other measurements where people think that they've achieved fusion, and we go and we measure and we say there's nothing, and we say okay, and you just keep quiet about it. There isn't the controversy, there isn't the loss of face and so on. But it's difficult to make. It's a matter of degree. I think in this case, they were so the science that they'd done was so bad that this was out of balance, regrettable. Called a ghastly scientific mistake in some of the books.
What happened to Young's results? He was pipped at the post by this press conference by about a day, compared to the planned publication in Nature, I think, of their joint papers.
Jones from Brigham Young University.
I beg pardon, the name wrong.
Well, he published his paper. He was never claiming anything that was going to be an energy source or anything. His results of, he thought he detected neutrons which demonstrated that what he called piezoelectric, no, not piezo fusion, I think he called it, and he felt it was something to do with the pressure that was, and temperatures in the core of the Earth. So that was generally regarded as being okay. I know that subsequently, following the terrorist attack on the 11th of September, he became convinced that there was a conspiracy, and he published papers about the collapse of concrete buildings, and he felt that putting an aeroplane into a building wasn't sufficient to bring it to the ground. And he took voluntary retirement from Brigham Young University in about 2004 or something.
Okay, any more questions for Michael? Okay, let's thank Michael again.